Every so often, the universe does something subtle. No explosions, no flashing warnings, just a quiet signal drifting into our view, asking to be noticed. In mid-2025, astronomers saw exactly that. At first, it looked ordinary, a faint point of light moving slowly against the background stars. The kind of thing automated sky surveys record thousands of times every year. But this one was different. Its path didn't curve the way it should. It didn't obey the gentle gravity rules that guide comets born in our solar system. Instead, it moved with a confidence that suggested it didn't belong here at all. Within hours, calculations confirmed the suspicion. This object was not from the Kuiper Belt, not from the Oort cloud, not from anywhere the sun had ever controlled. It came from another star system. Astronomers named it 3I-ATLAS, the third confirmed interstellar visitor humanity has ever observed. To understand why this mattered so much, imagine living your entire life on a quiet island. Boats occasionally arrive, but they're always familiar. Same materials, same construction, same routes. Then one day, something arrives from beyond the horizon, built differently. Weathered by a journey no local vessel could survive. That's what 3I Atlas represented. A messenger from another stellar neighborhood. Unlike its predecessors, this visitor was massive. Estimates suggested it could be more than 5 kilometers across, large enough to preserve pristine material from the moment it formed. Size matters in space. Smaller objects are battered by radiation, their surfaces eroded by countless collisions. But large bodies keep secrets longer. They are time capsules. As 3I Atlas approached the sun, telescopes around the world turned toward it. Not one or two. Dozens. Ground observatories in Chile and Hawaii. Space telescopes orbiting far from Earth's interference. Even skilled amateur astronomers contributed precise measurements. For the first time, humanity wasn't just watching an interstellar object pass by. We were studying it in detail. As sunlight warmed its surface, frozen gases began to escape. A faint coma appeared. Chemical signatures revealed themselves in spectral lines. And that's when things became truly interesting. The comet was rich in carbon dioxide. Far richer than most comets born around our sun. It also contained complex organic molecules, not proof of life, but ingredients life often uses. Carbon-based chemistry is common in the universe, but seeing it preserved inside an object formed around another star told us something profound. The building blocks of planets, and possibly life, are not rare exceptions. They are part of the standard cosmic recipe. This object had formed billions of years ago, around a star we may never identify with certainty. Long before Earth had oceans. Long before life learned to breathe oxygen. For eons, it drifted through interstellar space, a region so empty that a cubic kilometer might contain fewer atoms than a laboratory vacuum. Then by chance, gravity nudged it. A subtle deflection here, a distant stellar encounter there, until its path crossed ours. The timing was perfect in a way that feels almost poetic. Wide-field surveys scanning the entire sky every night. Algorithms trained to detect motion patterns humans would miss. A century ago, 3I Atlas would have passed unnoticed. A ghost slipping through the solar system in silence. But in 2025, we were ready. One of the most important achievements was refining its trajectory. By tracking its speed and direction with extreme precision, astronomers could trace its path backward, not perfectly. Gravity distorts everything over time, but enough to estimate where it came from. Early models suggested a star system roughly 50 light-years away. That distance may sound enormous, but on a galactic scale, it's our neighborhood. This object began its journey before humans existed, before mammals dominated Earth, before dinosaurs vanished. It carried no intention, no message written in symbols, yet it told a story anyway. It showed us that star systems exchange material, that planetary debris doesn't stay home forever, that our solar system is not isolated. In fact, we likely send our own messengers outward. Jupiter's immense gravity occasionally flings comets away at escape velocity. Those objects become interstellar wanderers themselves. Some may pass near alien suns. Perhaps alien astronomers watch them the way we watched 3IATLAS, wondering where they came from. This realization changes how we think about planetary systems. They are not sealed laboratories. They are participants in a slow, ongoing cosmic exchange. And there's another reason this discovery mattered. Interstellar objects are the only samples of other star systems we can study directly. We cannot yet send probes to nearby stars. Even the closest would take thousands of years with current technology. But these objects come to us, free samples from distant worlds. Each one carries chemical clues about its birth environment, temperature, radiation, composition. With enough visitors, patterns emerge. We can compare, categorize, build a real understanding of how planetary systems form across the galaxy. Before 2017, interstellar objects were theoretical, possible, but unconfirmed. Now we have 3, and models suggest there are many more. Thousands may pass through the outer solar system at any given time. Most too small or too faint to detect. But technology improves, and detection rates will rise. The discovery of 3IATLAS also changed how astronomers operate. When the object was identified, observation time was allocated within hours. International teams coordinated instantly, data shared across borders and institutions. This level of rapid response didn't exist decades ago. Modern astronomy is no longer slow and solitary. It is global, connected, and fast, because interstellar visitors don't wait. 3.1 Atlas swung around the Sun and began its exit. By early 2026, it would fade beyond reach, never to return. This was humanity's only chance to study it, and we didn't waste it. The success reignited discussions about future missions, not passive observation, active interception. Imagine a spacecraft designed to launch quickly, stored, fueled, waiting. When the next interstellar object appears, it goes. Matching velocity, flying alongside, sampling material directly. The engineering challenges are enormous, but the reward would be historic, touching matter that formed around another star. For now, 3I Atlas remains a reminder. The universe is not static, not distant, not sealed away. It moves, it exchanges, it reaches into our solar system when conditions align. And sometimes, if we're paying attention, it leaves behind a story, a quiet one, written in chemistry, motion, and time. In Part 3, that story continues closer to home, not from another star, but from a planet we thought we understood. Because in 2025, even our own solar system revealed something it had kept hidden for decades. Thanks for watching, and be sure to subscribe so you don't miss what happens next. While astronomers were watching a messenger from another star slip back into the dark, something far closer was quietly revealing itself. Something we thought we understood, something we believed had already given up its secrets. It hadn't. In early 2025, a routine observation turned into a reminder of how deceptive familiarity can be. The planet was Uranus, cold, distant, tilted on its side like a fallen world. For decades, Uranus had been treated as a supporting character in the solar system. Too far, too quiet, too uneventful. We'd visited it once, briefly, when Voyager 2 rushed past in 1986, sending back a handful of images before disappearing into interstellar space. That flyby gave us our only close look. 10 new moons discovered, rings confirmed, magnetic oddities noted, then silence. Or so we thought. In February of 2025, the James Webb Space Telescope was aimed toward Uranus again, not to search for new moons, not to hunt for surprises. The goal was modest. Scientists wanted to study the planet's faint ring system and better understand its composition. Webb did what it does best. It looked longer. It looked deeper. It noticed what earlier instruments could not. Buried in the glare, drifting near the rings, was a faint point of light. Almost nothing, a whisper of reflected sunlight, too dim for Voyager, too small for most ground-based telescopes. But Webb saw it. Follow-up observations confirmed the suspicion. This wasn't noise. It wasn't a background star. It was moving, slowly, consistently, obeying Uranus's gravity, a new moon. They gave it a provisional name, S-2025 U1, just 10 kilometers across, about the size of a small city. In cosmic terms, barely a speck. And yet, its discovery mattered more than its size suggested, because Uranus was no longer finished. To understand why this was so significant, you need to understand how moons tell stories. Large moons are loud. They dominate attention. They shape rings. They stir tidal forces. But small moons are archivists. They preserve the scars of ancient collisions. They record the gravitational chaos of a planet's past. S-2025 U1 belongs to a class called irregular moons. These moons don't orbit neatly along a planet's equator. Their paths are tilted, elongated, sometimes even backwards. They are not children of the planet. They are adoptees, captured objects. Long ago, Uranus passed through regions filled with debris, asteroids, fragments, remnants of planetary formation. Some wandered too close, gravity grabbed them, and they stayed. But capture is rarely gentle. Objects collide, break apart, scatter. Families of moons form from shattered parents. By mapping the orbit of S-2025 U1, astronomers noticed something intriguing. Its path aligned with a known cluster of irregular moons. Not random, not accidental. This moon was likely a fragment, a survivor of a much older collision, a piece of a larger object that no longer exists. This tells us Uranus's past was violent, more violent than its calm blue appearance suggests. And there was more. Uranus's rings are narrow and faint, nothing like Saturn's bright bands. Scientists have long suspected these rings are maintained by shepherd moons' small objects, whose gravity keeps ring particles confined. S-2025 U1 might be one of them. If so, it isn't just a passive rock drifting in space. It's actively shaping its environment, quietly sculpting a ring that stretches tens of thousands of kilometers. That's the thing about small moons. They don't announce themselves. They influence, slowly, persistently, over millions of years. The discovery also highlighted something deeper. Our map of the solar system is incomplete. Jupiter has over 90 known moons. Saturn now has more than 200. Uranus has 29. Neptune 16. These numbers are not final. They are temporary. Each improvement in detection reveals more, smaller, fainter, harder to see. There are likely hundreds more moons orbiting the giant planets, too small to reflect much light, too dark to stand out against space, and Webb is beginning to reveal them. This raises an uncomfortable truth. If we are still discovering moons around planets we've known for centuries, what else are we missing? Asteroids, transient objects that linger quietly near Earth, subtle gravitational structures shaping orbits without being seen. 2025 became a year of rediscovery, not of new places far away, but of our own backyard. The implications extend beyond Uranus. Every new moon adds complexity to mission planning. Future spacecraft need accurate maps. Every small body is a potential hazard or an opportunity. Some moons may hold clues to the early solar system's chemistry. Others may contain water, ice. Some may even serve as stepping stones for future exploration. Uranus itself is becoming increasingly interesting. It represents a class of planets we barely understand, ice giants. More than half of the exoplanets discovered so far resemble Uranus or Neptune in size. If we want to understand those distant worlds, we must first understand our own. A dedicated Uranus orbiter has been proposed, a mission that would spend years studying the planet, its atmosphere, rings, and moons. Discoveries like S2025U1 matter because they arrive before the mission launches. You can't study what you don't know exists. Better maps lead to better missions, and better missions lead to better understanding. There's something poetic about this discovery. A moon so small it escaped notice for decades, found not by searching for it, but by looking carefully at something else. That's how many discoveries in 2025 happened. You look for one thing, the universe gives you another. Webb was built to look back in time, to see the first galaxies, the birth of stars, the dawn of structure. But here it was, revealing something quietly orbiting a planet in our own solar system. It's a reminder that exploration doesn't always mean distance. Sometimes it means attention. As astronomers catalogued the orbit of S2025U1, another realization settled in. Our picture of the solar system is still evolving, still incomplete, still surprising. And if Uranus can hide moons, then other planets can hide secrets, too. Which leads to an even bigger question. If small worlds can escape our notice so easily, what about signs of life? What if life doesn't shout? What if it whispers? That question would soon become unavoidable. Because later, in 2025, a rover on Mars would find something that forced scientists to reconsider a question older than astronomy itself. Are we alone? But that story belongs to part 4. Thanks for watching, and remember to subscribe for the next chapter. There's a moment in science when excitement quietly turns into discomfort. In 2025, that moment arrived when astronomers realized They were looking at a black hole that simply should not exist, at least not according to everything we thought we knew. Another possibility involved extreme merger rates. In the crowded, chaotic early universe, galaxies were packed much closer together. Collisions were frequent and violent. In this cosmic mosh pit, black holes might have merged with each other far more rapidly than they do today, growing exponentially instead of in a straight, linear fashion. They weren't just passive passengers along for the ride. They were cosmic architects. This changes how we think about the formation of all cosmic structures. It suggests that galaxies didn't simply grow and then acquire black holes later on. It's possible that the black holes came first and helped their host galaxies grow around them. A feeding black hole can regulate star formation in its galaxy. Too much radiation, and it can blow away the gas needed to form new stars. Too little, and star formation can run wild. A delicate balance has to exist. Finding that balance so early in cosmic history suggests the universe reached a state of complexity far faster than we ever expected. There's also a deeper, more unsettling implication. If supermassive black holes formed this early and merged this often, they should have produced powerful gravitational waves, not the kind detected by observatories like LIGO, which are tuned to the mergers of smaller, stellar mass black holes. No, these would be much deeper, lower frequency waves, a constant, low background hum echoing through space-time itself. Future, space-based observatories, and if they do, it will be the confirmation that the early universe was full of massive black hole mergers. A cosmic symphony, still playing faintly beneath everything we see. The discovery in 2025 didn't answer these profound questions, but it made them unavoidable. It forced cosmologists to re-examine assumptions they had treated as settled for decades, to question their timelines, to revisit their equations. This is how science progresses, not by stubbornly defending old ideas, but by letting them break when the evidence demands it. And perhaps most importantly, this discovery reminded us of something very simple. The universe doesn't care what we expect. It doesn't follow our models out of courtesy. It doesn't slow down just because our theories need more time to catch up. It reveals itself as it is. And sometimes that revelation feels like a direct challenge to everything we thought we knew. While astronomers were grappling with these impossible black holes at the very edge of time, Another discovery in 2025 brought our attention back to something much closer, quieter, and deeply personal. A world just 18 light-years away. A planet that might just be habitable. A place that could one day change how humanity sees itself in the cosmos. Thanks for watching. If you enjoyed this journey into the unknown, be sure to like this video and subscribe for more deep dives into the mysteries of our universe. They glow as they feed, they scream in quasars, they launch jets that carve space for thousands of light years. That's how we've always found them. Supermassive black holes, the monsters lurking at the heart of galaxies. But what if they just stopped? What if they went completely silent? In 2025, astronomers discovered something that broke every rule. A black hole that made no sound at all. No radiation, no flares, no warning. It was hiding in a place we thought we knew, like the back of our hand, the Large Magellanic Cloud. If you're in the southern hemisphere, you can see it with your own eyes. It looks like a soft, cloudy patch floating near the Milky Way. It's a dwarf galaxy, orbiting our own from about 160,000 light-years away. That's practically next door in cosmic terms. Close enough that we can see its individual stars. Close enough that we thought there were no major surprises left. We were wrong. This whole story didn't begin with a black hole. It began with stars moving way too fast. For over a decade, a space observatory named Gaia has been quietly measuring the positions and motions of billions of stars with incredible precision. Gaia doesn't take dramatic photos. It just gives us numbers, tiny changes in position, recorded over and over. Most stars drift along calmly, following predictable orbits. But every now and then, Gaia spots something strange. A star racing through space much faster than it should be. We call these hypervelocity stars. They're rare, and they usually have a violent backstory. To get that kind of speed, a star needs a powerful gravitational kick, almost always from a supermassive black hole. So, in early 2025, researchers were analyzing the latest Gaia data, and they noticed something deeply unsettling in the Large Magellanic Cloud. It wasn't one hypervelocity star. It was dozens. And they weren't just moving randomly. When the scientists traced their paths backward in time, all their trajectories converged on the same single, invisible point near the galaxy's center. Imagine shrapnel flying away from an explosion. That's what it looked like. Except there was no explosion, no light, no radiation, just motion. The only thing that could fling that many stars at such high speeds is an enormous gravitational force. Something with the mass of hundreds of thousands of our suns, all compressed into a space smaller than our solar system. There's only one thing in the universe that can do that. A supermassive black hole. Immediately, astronomers pointed every telescope they could at the spot. Optical, infrared, X-ray, radio, everything, and they found nothing. No glowing disk of gas. It was a complete blank. But the stars told a different story. The stars screamed that something massive was there, something dark, something dormant. Based on the motion of the stars, they estimated its mass at around 600,000 times that of our Sun. Now, that's smaller than the black hole at the center of our Milky Way, but it's enormous for a little dwarf galaxy like the Large Magellanic Cloud. This was the first time in history a supermassive black hole had been discovered, purely through its gravity, with zero electromagnetic signal. It was a sleeping giant. And that realization changed everything. Until then, nearly every supermassive black hole we knew about was found because it was actively feeding. Gas spiraling into a black hole heats up and shines with ferocious intensity, sometimes outshining entire galaxies. But feeding is a temporary state. When the fuel runs out, the black hole goes quiet. It becomes invisible. This discovery proved that the universe is likely filled with these silent giants. They aren't rare exceptions. They're common residents of galaxies, both large and small. We just didn't know how to find them. Now we do. This one discovery completely reshaped how we think about the evolution of galaxies. The Large Magellanic Cloud is what we call a low metallicity galaxy. Its stars have fewer heavy elements than stars in the Milky Way. This makes it a great stand-in for galaxies in the early universe. Finding a supermassive black hole there suggests that these massive objects can form much earlier and more efficiently than our theories predicted. And that ties directly into another major puzzle, one uncovered by the James Webb Space Telescope. Webb has been finding galaxies that look surprisingly mature, very early in cosmic history. Galaxies that already have organized structures, tons of new stars, and massive central black holes, all when the universe was less than 1 billion years old. How did they get so big, so fast? The silent black hole next door became a local laboratory for understanding that process. It suggests that black holes don't always need to grow slowly over billions of years. Under the right conditions, maybe they can just form big right from the start. But there's another implication, one that's a little harder to ignore. Our Milky Way is slowly pulling in the Large Magellanic Cloud. Over the next few billion years, the dwarf galaxy will be torn apart, its stars scattered and absorbed into our own, and its black hole, it's coming with them. Our galaxy has swallowed many smaller galaxies in its past. Each one might have brought its own dormant black hole. Some could be quietly orbiting in the Milky Way's outer halo right now. Others may have already merged with Sagittarius A*, the supermassive black hole at our galactic center. The universe might be far more crowded with these invisible behemoths than we ever imagined, and gravity is the only way to find them. This discovery also highlights a quiet revolution happening in astronomy, the power of big data. It's full of hidden mass. And this changes how we think about stability and even danger. A feeding black hole is obvious. You can see it from across the universe, but a dormant one, it's much harder to track. If galaxies are full of these objects, their gravitational influence is subtly shaping stellar orbits, star formation, and the entire structure of galaxies in ways we are only now beginning to grasp. Black hole astronomy is entering a brand new phase, an era where darkness itself becomes the evidence. But while this discovery looked to our galactic neighborhood, another, in 2025, forced astronomers to look much farther back, toward the very beginning of time, because the Webb telescope found a black hole that shouldn't exist at all, one that was already ancient and massive when the universe was still just an infant. And that discovery threatens to rewrite the opening chapters of cosmic history itself. Black holes usually scream for attention. They blast out X-rays, they blaze with radiation, they tear apart matter so violently that we can see them from across the universe. That's how we're used to finding them. But in March of 2025, astronomers found one that did none of that. No light, no jets, no warning, just stars running for their lives. The discovery happened inside the Large Magellanic Cloud, a small, irregular galaxy orbiting our own Milky Way. From the southern hemisphere, it's visible to the naked eye as a faint, cloudy patch in the sky, close by galactic standards, familiar and hiding something enormous. The key to this discovery wasn't light, but motion. For more than a decade, the European Space Agency's Gaia spacecraft has been mapping the positions and movements of stars with extraordinary precision, not just where stars are, but how they drift, wobble, and accelerate over time. Gaia doesn't just take pictures, it measures reality. Most stars move calmly, following predictable orbits. But occasionally, Gaia detects something strange. A star moving far too fast for its surroundings. These are called hypervelocity stars. They don't belong where they are. Their speeds are too extreme. Something has violently flung them outward. In early 2025, researchers noticed something unsettling in the Large Magellanic Cloud. Not one or two hypervelocity stars, but dozens. And when they traced their paths backward in time, every single trajectory pointed to the same invisible location near the galaxy's center. It looked like a crime scene reconstruction. Every escape route led back to the same suspect. But when astronomers pointed their telescopes there, they saw nothing. No glowing accretion disk, no radio emissions, no X-rays, just darkness. Yet the physics was unavoidable. To accelerate stars to those speeds, the object responsible had to be incredibly massive. Hundreds of thousands of times the mass of our Sun, all packed into a region smaller than our solar system. There is only one thing in the universe that fits that description: a dormant, supermassive black hole. This one weighs roughly 600,000 suns, and it had gone completely quiet. This discovery was revolutionary for one simple reason. It proved that the universe is full of black holes we cannot see. Until now, nearly every supermassive black hole we've found revealed itself by feeding. Matter spiraled in, and radiation poured out. They were cosmic beacons. This one was a ghost, a black hole that had run out of food, a dragon asleep because the pantry was empty. And yet its gravity still ruled everything nearby. The Large Magellanic Cloud is smaller and less chemically enriched than the Milky Way. Its stars contain fewer heavy elements. That matters because this metallicity affects how stars live and die. In low-metal environments, massive stars lose less mass through stellar winds. They collapse more completely. They leave heavier remnants behind. Finding a supermassive black hole in such an environment forces scientists to rethink how black holes form and grow, especially in the early universe. It suggests that massive black holes might form more easily than we thought, or earlier, or more quietly. There's something unsettling about that idea. If this black hole hadn't flung stars outward, we might never have known it existed. How many others are hiding? Every galaxy the Milky Way has swallowed over billions of years likely carried its own central black hole. Silent mergers, invisible additions to our galaxy's mass. Our own Milky Way may contain multiple dormant giants drifting unseen through its halo. Gaia's discovery marked a turning point. For the first time, astronomers had found a supermassive black hole purely through its gravitational fingerprint, not by what it emitted, but by what it disturbed. This method opens a new chapter in astronomy, a future where darkness itself becomes observable, where mass is mapped not by light, but by motion. The discovery also tells a story about cosmic evolution. The Milky Way is slowly consuming the Large Magellanic Cloud. In a few billion years, it will be torn apart, its stars absorbed into our galaxy. And its silent black hole, it will join ours. Two giants, drifting closer over cosmic time, destined to merge in the deep future. When that happens, they will release gravitational waves powerful enough to ripple space-time itself. Not light, not sound, but a vibration in the very fabric of the universe. Future observatories, like LISA, will be able to detect those waves, listening to the echoes of ancient mergers long after they occur. This discovery also highlights how astronomy is changing. It wasn't made by a single dramatic observation. It emerged from years of data, refined algorithms, and machine learning systems trained to notice what humans might miss. Computers flagged unusual motions, and humans asked why. Together, they revealed something hidden in plain sight. The Large Magellanic Cloud black hole reminds us of a hard truth. Most of the universe is invisible, not because it's mysterious, but because it's quiet. We tend to focus on what shines, but gravity doesn't need light to be powerful. It works patiently, relentlessly, leaving signatures only for those who know how to look. As 2025 unfolded, it became clear that the universe was not just revealing new objects, it was revealing new ways of seeing. Black holes without light, life without certainty, worlds without familiarity. And still, the surprises weren't finished. Because while nearby galaxies hid silent giants, the early universe was about to challenge everything we thought we knew about time itself. In Part 10, we travel back to a moment when the universe was barely awake and already building monsters. Thanks for watching. If you enjoyed this journey into the cosmic dark, be sure to like and subscribe for more. Sometimes the most important discoveries don't arrive with explosions, no flashing alerts, no dramatic countdowns, no headlines screaming revolution. Sometimes they arrive quietly, without anyone really noticing at first. In October of 2025, astronomers announced the discovery of a rocky planet orbiting a small, dim star just 18 light-years away. In cosmic terms, that distance is almost intimate. It's close enough to feel real, close enough to imagine. They named it GJ 251c. At first glance, it sounded like just another catalog entry. Another planet, another data point in a list that now contains thousands of worlds. But the more scientists studied it, the clearer it became that this planet was different. Not because it was Earth-like, but because it was reachable, at least in our imagination. 18 light-years is still impossibly far for us today. Even our fastest spacecraft would take tens of thousands of years to get there. But in the grand scale of the galaxy, it's next door. It's a place that future generations, with technologies we can only dream of, might actually plan missions toward. And that simple fact changes how we think about it. It transforms it from an abstract idea into a potential destination. The star at the center of this system, GJ 251, is a red dwarf. Red dwarfs are the quiet majority of the universe. They're small, cool, and incredibly long. In fact, they make up nearly 70% of all stars in our Milky Way galaxy. They burn their fuel slowly, steadily, for trillions of years. To put that in perspective, our sun will live for about 10 billion years. A red dwarf can shine for 1,000 times longer. If life wants time, an abundance of it, red dwarfs offer it, but they also come with challenges. Because red dwarfs are so dim, their habitable zones, the regions where a planet could support liquid water, sit very close to the star. Planets have to orbit tightly to receive enough warmth. That proximity often leads to a phenomenon called tidal locking. This means one side of the planet always faces the star, while the other side remains in permanent, frozen darkness. At first, that sounds incredibly hostile. A scorched, eternally sun-blasted dayside, and a frigid, lifeless nightside. But nature is rarely that simple. Computer models suggest that on such worlds, a narrow band can exist between the day and night, a twilight zone, a region of perpetual dawn or dusk, where the temperatures could be just right, allowing liquid water to persist. It's in this sliver of balance that life might find a foothold. GJ 251c orbits its star every 54 days. Its year lasts less than 2 of our Earth months. It's classified as a super-Earth, meaning it has about 4 times the mass of our planet. That doesn't mean it's a gas giant like Jupiter. It's still a rocky world, solid, a world you could, in theory, stand on. Of course, the gravity there would be stronger. Movement would feel heavier. Every step would be a constant reminder that this planet is not Earth, and yet it sits right in the middle of its star's habitable zone. That's what made scientists pause. That's what made this discovery so compelling. The planet was detected using something called the radial velocity method. Astronomers didn't see the planet directly. Instead, they watched the star, GJ 251, wobble ever so slightly as the planet's gravity tugged on it. This created a rhythmic shift in the star's light, a pattern repeating every 54 days. The signal was clean, repeatable, real. Follow-up observations confirmed it. This wasn't just random noise. This was a world. But what truly elevated GJ 251c from an interesting find to a prime target for future study was its potential for atmospheric analysis. At just 18 light-years away, it's close enough that future telescopes, like the successors to the James Webb Space Telescope, could actually analyze its atmosphere, if it has one. Here's how it would work. When the planet passes in front of its star from our perspective, an event, called a transit, the starlight filters through the planet's air. Molecules in that atmosphere leave fingerprints in the light, specific patterns that we can read. These fingerprints could reveal the presence of water vapor, carbon dioxide, methane, and even oxygen. On Earth, oxygen is especially important. It's a highly reactive gas, and it doesn't stick around for long on its own. It has to be constantly replenished, and on our world, the overwhelming source of that replenishment is life through photosynthesis. So, If we found significant amounts of oxygen in the atmosphere of an exoplanet, especially alongside gases like methane in an unstable combination, it would be incredibly difficult to explain without biology. Not impossible, but very, very difficult. GJ 251c might offer us the chance to run that very test, and that's why it matters. Not because it proves life exists elsewhere, but because it gives us a concrete, tangible place to look seriously. There's something emotionally different about nearby worlds. Distant galaxies are beautiful, but they're abstract. The light we see from them left before Earth even existed. They belong to deep history. Nearby planets, on the other hand, feel personal. They orbit stars we can name, stars that will still be shining long after our civilization changes or disappears. They invite us to ask a question that humans have always asked: if we had the technology, if we had the time, if we had the courage, could we go? Of course, red dwarf planets raise difficult questions about habitability. These stars are known to flare violently, especially when they're young. These flares can release massive bursts of radiation that could strip a planet of its atmosphere or sterilize its surface. Any life on such a world would need protection. A strong magnetic field, a thick atmosphere, or maybe life would exist underground or deep beneath oceans. But we must remember, life adapts. On Earth, it thrives in the most extreme environments imaginable. In superheated volcanic vents on the ocean floor, in the frozen tundra of the Antarctic, and under the crushing pressure of the deepest trenches, life survives radiation, heat, cold, pressure, and darkness. The universe has never promised comfort, only opportunity. GJ 251c also reminds us of scale. There are hundreds of billions of stars just in our Milky Way galaxy. If even a small fraction of them host rocky planets in their habitable zones, then worlds like this one are common. They're not rare miracles, not cosmic flukes. They are standard, expected outcomes of planetary formation. That realization quietly reshapes everything. It suggests that life itself might not be exceptional. It might be expected. We may not be unique observers in a silent universe, but just one voice among many scattered across countless worlds, each looking up at different skies and asking the very same question: are we alone? The discovery of GJ 251c didn't answer that question, but it made the question feel closer, less philosophical, and more practical. This is a planet that future astronomers will return to again and again. With each new telescope, with each new method, each new generation of instruments will sharpen the picture. One day, we might know what its skies look like. We might know whether clouds drift across its twilight zone, whether oceans exist on its surface, and whether the chemistry there ever crossed the incredible line into biology. And if it did, if life emerged independently twice in one small region of the galaxy, that would mean the universe is absolutely alive with possibility. As the year 2025 continued, discoveries piled up: hidden black holes, ancient galaxies, strange visitors from other star systems. But GJ 251c stood apart, not because it was dramatic, but because it felt reachable in the mind. A quiet world, a nearby star, a future target. And while astronomers were turning their attention outward, measuring distant worlds and ancient light, another discovery that year forced humanity to look inward, to our own solar system, to Mars. and to a single rock that might carry a memory older than any human civilization. That story unfolds in Part 8. Thanks for watching. If you enjoyed this journey, be sure to subscribe for more explorations into the cosmos. Mars has always been the quiet planet. No oceans crashing against shores, no wind carrying distant voices, no signs of life scurrying across the landscape. For as long as we've known it, Mars has been a world of dust, stone, and an almost absolute silence. And yet, in September of 2025, that silence suddenly felt thinner than it ever had before. NASA scientists made an announcement that sent shockwaves through the scientific community. A rock, collected by the Perseverance rover inside Jezero crater, had reached a troubling, thrilling milestone. After months of painstaking analysis, researchers had ruled out every simple, non-biological explanation they could imagine for its strange features. They were incredibly careful with their words. They did not say they had found life, but they said something just as important. They said the possibility of ancient life on Mars was now stronger than ever. The rock is known as Shayava Falls. At first glance, it's a small, unremarkable-looking sample. The kind of stone you might step right over without a second thought if it were on Earth. But context is everything. Shayava Falls was collected from Jezero crater, a location chosen with extreme deliberation. Billions of years ago, Jezero wasn't a crater at all. It was a lake. Rivers flowed into it, carrying sediment that settled gently at the bottom. Minerals formed, layer by layer, in the water. Here on Earth, places just like this preserve signs of life exceptionally well. So, if Mars ever hosted life, even for a brief moment in its history, Jezero crater would be one of the most likely places it left a trace. That's precisely why Perseverance was sent there. Not to search randomly, but to read a very specific chapter of Martian history. When the rover examined Shayava Falls up close, it found something completely unexpected. The rock contained small, dark spots scattered across its surface, each surrounded by lighter mineral halos. Scientists gave them a nickname: leopard spots. The spots themselves were found to contain organic molecules. These are carbon-based compounds, the fundamental building blocks of chemistry we associate with life. Now, finding organic molecules alone is not proof of life, not even close. They're actually quite common throughout the universe. Meteorites that fall to Earth contain them. Comets are full of them. They can form through perfectly normal chemistry, no biology required. But it was the arrangement that mattered. These organic-rich spots were encased in minerals that typically form when water interacts with rock. The whole pattern looked strikingly similar to features found on Earth that are created by microbial activity. Not identical, mind you, but uncomfortably close. Back in 2024, when these features were first spotted, scientists were cautious. They proposed all sorts of alternative explanations. Maybe it was just some unusual chemical reactions, or strange geological processes we hadn't seen before. Maybe it was contamination from space debris. Science, after all, demands skepticism. Extraordinary claims require extraordinary evidence. So they spent the next year testing those alternatives. Again and again and again. By September of 2025, many of those other explanations had failed. The chemistry didn't match what we see in typical Martian meteorites. The mineral structures didn't align with known non-biological reactions. The organization of the features, the leopard spots, seemed far too structured to be random chance. Imagine you're walking on a beach and find footprints in the wet sand. At first, you might think it's just erosion, or the way the water washed over the shore. But as you rule out each of those possibilities, the simplest explanation starts to feel unavoidable. Something walked here. Shayava Falls reached that stage. It wasn't proof, but it was pressure. Intense pressure on our assumptions about Mars. Pressure on our scientific models. Pressure on the long-held idea that Mars was always, and has always been, lifeless. Mars today is a cold, dry, hostile world. But ancient Mars was a completely different place. We know this. Rivers carved deep valleys, lakes filled craters, liquid water moved freely across the surface. And here on Earth, there's a simple rule. Where there is water, there is life. Almost without exception. If life arose independently on Mars, even if it was simple and died out billions of years ago, it would change everything we think we know. It would mean that life isn't fragile or rare. It would mean that chemistry naturally leans toward biology whenever the conditions are right. It would mean the universe isn't a sterile, empty void, but a fertile ground for life. But here's the problem. Shayava Falls is still on Mars, more than 100 million miles away. The Perseverance rover carries an incredible suite of instruments. It has lasers, spectrometers, and powerful microscopes. It can analyze rocks in astonishing detail for a robot on another planet. But it cannot do what a full laboratory on Earth can do. It can't slice the rock into ultra-thin sections to examine its internal structure. It can't look at the features at the nanometer scale. It can't run the exhaustive range of chemical and isotopic tests needed for a final verdict. That's why this discovery reignited a sense of urgency around the Mars Sample Return mission. This is the multi-stage plan to bring Martian rocks back to Earth. Perseverance has been carefully collecting core samples, sealing them in sterile tubes, and storing them for a future retrieval mission. Shayava Falls is one of them. If and when those samples return to Earth, scientists from all over the world will get to examine them independently. Geologists, chemists, biologists, astrobiologists, every possible test will be run, every method applied. Every alternative explanation will be challenged with the full force of modern science. Only then will we know for sure. And that's why scientists are being so careful right now. They refuse to declare victory prematurely. It's not because they lack excitement. Believe me, they are bursting with it. It's because the stakes are just too high. A false positive would damage public trust in science for generations. A rushed conclusion would undermine decades of careful, methodical work. Science has to move slowly when the truth really matters. The implications of this reach far beyond Mars. If life did arise twice, independently, in just one solar system on Earth and on Mars, then life is likely common across the galaxy. Planets with water would no longer be seen as rare cosmic lottery tickets, but as expected outcomes. Every red dwarf system, every rocky world in a habitable zone, every quiet star with planets orbiting in a stable balance, they all become candidates for life. Suddenly, the universe starts to feel a little more crowded. And even if Shayava Falls ultimately turns out to be a product of some exotic, non-biological process, the discovery is still monumental. It proves that ancient Mars had complex organic chemistry. It proves the planet was active, dynamic, and potentially habitable. It helps us refine where we should look next. Other ancient lakebeds, fossilized river deltas, the remnants of ancient hydrothermal vents. Mars is not a dead world. It is a world with a deep, hidden memory, and we are only just beginning to learn how to read it. There's something profoundly human about this entire search. In a way, we are looking for ourselves. Not literally, of course, but for our place in the cosmos. We want to know whether life is a one-time miracle or a natural process. We want to know if consciousness is a rare fluke or an inevitable outcome. We want to know if the universe is fundamentally indifferent or if it's quietly, persistently creative. The rock named Shayava Falls doesn't answer those questions yet, but it brings them into sharp focus. It takes them from the realm of philosophy and brings them squarely into the world of science. As 2025 continued, the year refused to slow down. While Mars whispered hints of ancient biology from its dusty past, another discovery that same year revealed a massive, hidden presence hiding in plain sight. Not on Mars, not even in our own galaxy, but in a neighboring one. A black hole that wasn't screaming with light, wasn't feeding on stars, wasn't shining at all. It was just sitting there, silently flinging stars into the darkness. That story begins in our next video. Thanks so much for watching. If you're as fascinated by these discoveries as we are, make sure you subscribe and hit the bell so you don't miss what's coming next. We'll see you in the next one. There's a problem with time. Not our time, but cosmic time. According to everything we thought we understood, some things in the universe should take a very, very long time to form. We're talking hundreds of millions, sometimes billions of years. And yet, in 2025, astronomers found something that, by all rights, simply shouldn't exist. A fully grown supermassive black hole, actively feeding inside a galaxy that existed just 570 million years after the Big Bang. To understand just how shocking that is, imagine this. The universe is about 13.8 billion years old today. At 570 million years, it was still an infant, barely 4% of its current age. The cosmos was a chaotic place, no mature galaxies, no long-settled structures, and certainly not enough time for slow, gradual growth. Or at least, that's what we believed. The galaxy is known as Canucks, LRDZ 8.6. It appeared as a faint, reddish smudge of light detected by the James Webb Space Telescope while it was staring deep into the cosmic dawn. When astronomers analyzed that faint light, they found unmistakable signatures. They saw hot gas spiraling inward at incredible speeds. They detected an extreme output of energy. These are patterns only produced by one thing: matter falling into a black hole. And this wasn't just any black hole. It was a monster weighing millions of times the mass of our sun. This shouldn't be possible. Our standard models say that black holes begin small, formed from the collapse of massive stars. Then, they grow slowly, over eons, by merging with other black holes and feeding on surrounding gas and dust. That process takes time, a lot of time. But here was a black hole that was already enormous, already active, when the universe had barely figured out how to make stars. It's like finding a fully constructed skyscraper in a town that has uneven invented bricks yet. Galaxies were packed close together, and cosmic collisions were common. In this chaotic environment, black holes might have merged repeatedly, building mass in a rapid cosmic frenzy. Either of these explanations would completely reshape our understanding of how the first large structures in the universe formed. And this black hole wasn't a lone freak of nature. Webb has been finding too many surprises in the early universe. We're seeing galaxies that are too big, too organized, and too mature for their age, all of them appearing far too early. We're finding spiral structures in an era when chaos should have dominated. We're seeing brilliant black holes shining where we expected only darkness. It's as if the universe wasted absolutely no time getting organized. This matters because supermassive black holes are not just passive objects, they actively shape their environment. As they feed, they blast out radiation so powerful that it can ionize hydrogen gas across vast distances. This process, called cosmic reionization, is what ended the universe's dark ages. Before reionization, the universe was opaque, filled with a fog of neutral hydrogen that absorbed light. Afterward, it became transparent, just as it is today. Stars could finally shine freely, and galaxies could be seen across cosmic distances. Finding such massive black holes so early suggests that reionization may have happened much faster and differently than we thought. The universe didn't slowly wake up, it snapped awake, with these cosmic giants helping to flip the switch. And there's another profound implication. If supermassive black holes formed this early and this often, then their mergers should have created a gravitational wave background, a constant, low-frequency hum in the fabric of space-time itself. These are the faint ripples from countless ancient, violent collisions. Future observatories are being designed right now to listen for that hum. And if they hear it, this discovery will have been the first warning shot. The early universe wasn't a fragile, slow-moving nursery. It was efficient. It was aggressive. It was incredibly creative. Matter organized itself faster. Large structures formed earlier. And cosmic giants appeared long before we thought they had any right to. Because science advances not when our models succeed, but when they fail spectacularly. As 2025 continued, it became clear that this was not a year for small corrections. It was a year for major revisions. A year for compressing timelines and questioning our most basic assumptions. And still, the surprises weren't finished. Because even as the early universe revealed its impossible giants, something equally unsettling was appearing slightly later in cosmic time. A galaxy with arms, not vague shapes or blurry hints, but clear, well-defined spiral structure formed far, far too early. That story unfolds in our next episode. Thanks for watching, and be sure to subscribe so you don't miss it. Some of the greatest discoveries don't come from distant galaxies shining at the edge of time. They come from places we thought we already understood, right here in our own cosmic backyard. Between the orbits of Mars and Jupiter lies the main asteroid belt, a vast region filled with millions of rocky fragments circling the Sun. These are the remnants from the early days of our solar system, the leftover building blocks that never quite managed to form a planet. For decades, astronomers looked at this region and believed it held few surprises. They were wrong. In April of 2025, A revolutionary new chapter in our exploration of the solar system began. NASA's Lucy spacecraft flew past a small, unassuming asteroid named Donald Johanson. Now, this wasn't the mission's main event. It was more like a dress rehearsal, a crucial test encounter on a much longer and more ambitious journey. But what Lucy saw that day completely changed how scientists think about how asteroids are born and how they evolve over billions of years. The spacecraft itself is named after the famous fossil, Lucy, the Australopithecus skeleton, that fundamentally reshaped our understanding of human origins. The name is no accident. This robotic explorer was built to study the fossils of our solar system, ancient objects that preserve the pristine earliest history of how everything around us came to be. Lucy's primary targets are the Trojan asteroids. These are mysterious clusters of objects that share an orbit with the giant planet Jupiter. Perfectly trapped in gravitational balance points, one group leading the planet and one group trailing behind. Scientists believe these Trojans are time capsules, largely unchanged for over 4 billion years. They are frozen relics from the dawn of the solar system. But before Lucy could reach these distant targets, it first had to navigate through the main asteroid belt, and that's where Donald Johanson was waiting. From Earth, it looked like nothing special, a tiny object, only a few kilometers across. It was too small to have pulled itself into a sphere, and too faint for our telescopes to reveal much detail. But when Lucy zipped past it at over 5 kilometers per second, its powerful cameras captured something truly unexpected. The asteroid wasn't a single, solid body. Instead, it was shaped like a peanut. 2 distinct lobes were gently pressed together, joined by a narrow neck of material. This strange shape tells a fascinating story. Donald Johanson is what scientists call a contact binary. This means one of 2 things happened. Either 2 separate asteroids slowly drifted into each other, gently collided, and stuck together, or a single, larger body was somehow fractured and then slowly reassembled itself over eons. This is a huge deal. Collisions in space are usually incredibly violent. Think of cosmic demolition derbies. Objects smash into each other, shattering into countless fragments that scatter across the solar system. A gentle collision, one that allows 2 bodies to merge, suggests very low relative speeds. It paints a picture of a much calmer, more orderly environment in the early solar system than we previously imagined. An environment where ancient materials could combine and grow rather than just being constantly destroyed. Lucy's incredibly detailed images also revealed a landscape covered in craters. Each one is a scar from a past impact, a record of its long and violent history. By carefully counting and measuring these craters, scientists can estimate how long the asteroid's surface has been exposed to the harsh environment of space. The surface of Donald Johanson tells a story of incredible survival. It has been hit, it has been reshaped, but through it all, it has endured. This little asteroid likely formed during the chaotic early period when the planets themselves were still assembling. It has been a silent witness to the formation of Earth, the birth of our moon, and the great migration of giant planets like Jupiter. And in its very structure, it remembers it all. Perhaps one of the most intriguing findings was about the asteroid's internal structure. It appears to be a rubble pile. It's not a solid chunk of rock, but rather a loose collection of boulders, gravel, and dust, all held together by its own incredibly weak gravity. This discovery changes how we think about the resilience of asteroids. Rubble piles can absorb impacts in a completely different way than solid rocks. Instead of cracking apart, they flex and deform. The energy from an impact dissipates throughout the loose material. The damage is spread out rather than concentrated in one spot. This might be the secret to why so many asteroids survive what should be catastrophic, shattering collisions. And understanding this isn't just an academic exercise. It has very real, practical implications for planetary defense. If an asteroid similar to Donald Johanson were ever on a collision course with Earth, how we would try to deflect it would depend entirely on its internal structure. If we push a solid rock, it moves. But if you push a loose pile of rubble too hard, you might just break it apart, turning one big problem into many smaller, but still very dangerous, pieces. Understanding these flying rubble piles is critical to keeping our own planet safe. The flyby of Donald Johanson also served as a perfect validation of Lucy's instruments. Its cameras performed flawlessly. Its navigation systems were precise down to the meter. The data transmission back to Earth was smooth and clear. This success was essential because Lucy's real primary targets are still far ahead. Over the next decade, the spacecraft will visit multiple Trojan asteroids, each one thought to have originated from a different region of the early solar system. By studying them up close, one by one, we will piece together the grand story of how our planets formed, how they migrated to their current orbits, and how the solar system settled into the configuration we see today. Donald Johanson was the prologue to this epic journey, and it delivered a powerful message. The early solar system wasn't a neat, tidy place. It was messy, it was chaotic, but it was also creative and surprisingly efficient. Objects collided, both gently and violently. Material clumped together and scattered apart. And over millions of years, gravity sculpted that chaos into the beautiful, complex structure we call home. Lucy's first encounter showed us that even the smallest, most insignificant seeming objects in space preserve that incredible history. It proved that in the cosmos, nothing is truly insignificant. As the year 2025 progressed, it became increasingly clear that this was not just a year of cosmic revelations. It was a year of perspective, from galaxies in the distant universe forming impossibly early, to nearby asteroids preserving the solar system's most ancient memories. Every new discovery seemed to point to the same fundamental truth. We are surrounded by history, a history written in stone, written in motion, and written in light. And just when it seemed like the universe had shown us everything it could, for 1 year another familiar star, one we see with our own eyes almost every night, surprised astronomers by revealing a secret it had kept hidden in plain sight. A star we thought we knew so well. That story begins with the red giant, Betelgeuse, and it unfolds in our next video. Thanks for watching, and if you want to continue this journey through the cosmos, make sure you're subscribed. Spiral galaxies aren't supposed to be early. They're meant to be the result of patience, time, stability, billions of years of quiet, steady rotation. At least, that's the story we've told ourselves. But then, late in 2025, the James Webb Space Telescope showed us something that just didn't fit that story at all. It found a galaxy with clear, well-defined spiral arms, already in place, just 1.5 billion years after the Big Bang. They named it Alcnanda, a beautiful name for a deeply unsettling object. To understand why this matters, you have to understand how spiral galaxies form, or at least how we thought they formed. In the early universe, galaxies should be messy, chaotic. They should be irregular clumps of stars, still pulling themselves together. Gas clouds should be colliding, mergers happening constantly, gravity pulling in every direction at once. We believed order was supposed to come much, much later. You see, spiral arms require a stable, rotating disk. They arise from something called density waves, which are regions where stars and gas bunch up temporarily as they orbit the galaxy's center. These waves take a very long time to settle into those beautiful, coherent patterns we see. Our own Milky Way likely took several billion years to develop its familiar spiral structure, but Alaknanda did it in a tiny fraction of that time. Webb's images were not ambiguous. This wasn't some wishful interpretation. The arms were visible, they were structured, and they were actively forming stars. This galaxy looked mature at an age when the universe itself was still a restless toddler. It was like finding a fully finished, magnificent cathedral in a city that had only just figured out how to stack stones. Naturally, this discovery immediately raised some very uncomfortable questions. How did this galaxy manage to settle down so quickly? Where did it get the angular momentum needed to form a stable disk? And how did it avoid being torn apart by mergers long enough for those spiral arms to stabilize? One possibility lies in the universe's invisible scaffolding, dark matter. Galaxies form inside vast invisible halos of dark matter. The shape and behavior of those halos determine how gas flows, how stars form, and how structure emerges. It's possible that dark matter clumped more efficiently in the early universe than our models predicted. This could have created deep gravitational wells very early on, wells strong enough to organize matter rapidly and protect these growing galaxies from cosmic disruption. Another possibility is the environment. Perhaps Alaknanda was just lucky. Maybe it formed in a relatively quiet, peaceful region of space. Fewer collisions, fewer violent interactions. It had enough time to settle into order while its neighbors remained chaotic and messy. Or maybe, just maybe, our models simply underestimate how fast nature can organize itself. This wouldn't be the first time we've been wrong. Webb has repeatedly shown us that the early universe was far more efficient than we expected. Stars formed earlier, galaxies grew faster, black holes became massive sooner. Alaknanda fits that pattern perfectly. It's not an anomaly, it's a clue. The galaxy's star formation rate is also telling. It's active, but not wildly so. It's not burning through all its gas in some short-lived frenzy. Instead, its star birth appears balanced and regulated. That balance is incredibly difficult to achieve. Star formation creates enormous energy, radiation, supernova explosions. All these things can blow gas right out of a galaxy, shutting down any future star birth. But somehow, Alaknanda managed to keep forming stars while holding itself together. This suggests that complex feedback processes were already operating effectively far earlier than we ever thought possible. This discovery forces theorists to confront a possibility they've been avoiding for a while. Maybe the universe didn't just slowly crawl its way to complexity. Maybe it sprinted. If spiral galaxies like this can form so early, then the entire timeline of cosmic evolution compresses dramatically. What we thought took billions of years might have only taken hundreds of millions, and that affects everything. It changes our understanding of black hole growth, galaxy mergers, chemical enrichment, and even the emergence of habitable environments. The universe may have been ready for life far earlier than we ever imagined. And that leads to a rather unsettling thought. If complex galaxies formed quickly, then potentially habitable planets could have formed early too. Life, if it exists elsewhere, might have had a much longer head start than life on Earth. Civilizations, if they arise on other worlds, may have had billions of extra years to develop. That's not science fiction. That's a direct consequence of these accelerated cosmic timelines. Alaknanda also reminds us of something deeply human. We often assume that complexity requires a lot of time because we, as humans, require a lot of time to build complex things. But nature doesn't work on our schedule. When the conditions are just right, organization happens fast. Crystals can form in seconds. Storms organize themselves in hours. And galaxies, apparently, can organize themselves in what amounts to a cosmic instant. The universe doesn't hesitate. It builds. As astronomers continue to study Alaknanda, they'll look for more clues. They'll search for companion galaxies, for evidence of past mergers, for the gas flows that might be feeding its disk. Each new detail will help refine our understanding. But the damage to our old assumptions is already done. The early universe was not primitive. It was capable, creative, and incredibly efficient. As 2025 rolled forward, this theme became impossible to ignore. Hidden black holes, hints of ancient life, impossible cosmic timelines. Every new discovery seemed to be pointing in the same direction. We had seriously underestimated the universe. And just when it seemed we had reached the limit of surprise, another quiet mission delivered a stark reminder that even our own solar system still holds deep secrets, not far away and not ancient, but right here, right now. That story begins with a small spacecraft named Lucy, and that's the story we'll dive into next time. Thanks for watching. Some stars feel like old friends. They rise with the seasons. They anchor the constellations. We've named them, charted them, and watched them for centuries. We start to assume they have no secrets left, and then one of them proves us all wrong. In early 2025, astronomers confirmed something extraordinary about Betelgeuse, the bright red star marking the shoulder of Orion the Hunter. Betelgeuse is not alone. For decades, scientists had their suspicions. There were subtle irregularities in its brightness, small gravitational hints, patterns that didn't quite fit the model of a solitary star. But a suspicion is not the same as proof. That proof finally arrived thanks to the combined power of the James Webb Space Telescope and the Gemini Observatory. They peeled back the star's blinding glare and revealed a hidden partner. They even gave it a friendly nickname, Beetle Buddy. To understand why this is such a big deal, you have to understand Betelgeuse itself. It's a red supergiant, one of the largest stars you can see with your naked eye. It's absolutely colossal. If you were to place it at the center of our solar system, its fiery atmosphere would stretch out past the orbit of Mars, maybe even reaching Jupiter. Stars like Betelgeuse live fast and die violently. It started its life as a brilliant blue giant, perhaps 20 times more massive than our Sun. It burned through its hydrogen fuel at a furious pace, swelling up into the red supergiant we see today as nuclear reactions shifted deeper into its core. And one day, it will explode. It will go supernova. Now, probably not tomorrow, and not next year. But someday, in cosmic terms, it's right around the corner. You might remember back in 2019 and 2020, when Betelgeuse dimmed so dramatically that people all over the world noticed. They called it the Great Dimming. For a moment, it seemed like the long-awaited explosion might finally be happening. But it wasn't. The dimming was caused by a massive cloud of dust that the star itself had ejected, which temporarily blocked its light from our view. But that event left a lot of questions. Why does Betelgeuse behave so erratically? Why does it shed its own material in these unpredictable bursts? Well, the answer, it turns out, might be gravity. Specifically, the gravity of its newfound companion. Betelgeuse is a hot, blue-white star, estimated to be between 10 and 15 times the mass of our Sun. It orbits Betelgeuse very slowly, taking a few hundred years to complete a single circuit. But that slow cosmic dance is incredibly important. As the two stars circle each other, their mutual gravity creates powerful tidal forces within Betelgeuse. Think about how our moon pulls on Earth's oceans, creating the tides. Now imagine that on a stellar scale, Betelgeuse is constantly pulling on Betelgeuse's vast, gaseous atmosphere. But instead of water, these tides are acting on superheated plasma. They stretch the star. They destabilize its outer layers. They can trigger mass ejections, sudden outbursts, and those enormous dust clouds. It seems the Great Dimming may not have been a random event at all. It may have been a direct consequence of this celestial companionship. Finding Betelgeuse was an incredible technical challenge. Betelgeuse is just so blindingly bright. Its glare completely overwhelms anything nearby. It's like trying to spot a tiny candle sitting right next to a giant stadium floodlight. The James Webb Telescope overcame this by using a special device called a coronagraph. It essentially creates an artificial eclipse, blocking the star's intense central light so astronomers can see what's hiding in the glare. The Gemini Observatory then confirmed the finding using adaptive optics, a technology that corrects for the distortion of Earth's atmosphere in real time, giving them a crystal-clear view. Together, they finally pulled back the curtain of light. And there it was, a companion star, quietly shaping the fate of its giant partner. This discovery completely changes how astronomers think about Betelgeuse's future. When it finally does explode, the presence of a companion star could alter the entire dynamic of the supernova. It could affect how material is thrown out into space. It could even influence the shape of the beautiful nebula left behind. In some binary systems like this, the companion star actually survives the explosion, left to orbit a newly formed neutron star or black hole. In others, both stars are completely transformed. We don't yet know exactly what Betelgeuse's grand finale will look like, but we now know it won't be a solo performance. It's a good reminder that binary systems are actually very common in the universe. More than half of all stars are born with companions. Our Sun, being all by itself, is actually the exception, not the rule. The discovery of Betelgeuse teaches us something important. Even the brightest, most familiar objects in our sky can hide their deepest truths right behind a veil of familiarity. As 2025 continued, this theme would repeat itself again and again. The universe wasn't just revealing entirely new objects, it was revealing new relationships, hidden companions, invisible forces, and the quiet motions that shape the spectacular outcomes we can see. And while Betelgeuse's secret was unfolding high above our heads, something much, much closer to home was quietly joining Earth in its journey around the sun. It wasn't a moon, and it wasn't a man-made satellite. It was something far stranger. That story begins with an object that has been following us for decades, and it unfolds in our next episode. Thanks for watching. We often think of Earth as being on a solo journey, with just our one moon for company, tracing a clear path around the sun. But space, as it turns out, is rarely that straightforward. Imagine the surprise in August of 2025, when astronomers announced they'd found something that had been quietly tagging along with Earth for at least 60 years, maybe even longer. It's called 2025 PN7. And no, it's not another moon. It's something far more peculiar. 2025 PN7 is what scientists call a quasi-satellite. To wrap your head around that, picture two runners on a circular track. They aren't tied together, and they're not running around each other, but they maintain almost the exact same speed, so they stay close to one another, lap after lap. That's essentially what a quasi-satellite does. It orbits the sun, just like Earth does, but its orbital path is so perfectly synchronized with ours that from down here, it looks like it's circling our planet. For decades, this object moved silently through the cosmos, completely unnoticed. It was just too small, too dim, and too ordinary to catch anyone's eye. But then, thanks to upgraded sky surveys and advanced automated detection systems, something unusual finally popped up on the radar. When scientists ran the numbers, the results were stunning. 2025 PN7 has been orbiting with Earth for a minimum of 6 decades, and possibly for centuries. Its orbit is incredibly stable. It doesn't drift away, and it poses no threat of collision. It just follows us. The object itself is about 200 meters across, roughly the length of 2 football fields. If you could somehow stand on its surface, you'd feel almost no gravity. A single jump could send you floating off into space. It's basically a loose collection of rocks and dust, held together by its own weak gravity and shaped by ancient impacts. Most near-Earth asteroids are like cosmic commuters. They zip past us on long, stretched-out orbits, giving us a brief hello before disappearing into the darkness for years, or even centuries. 2025 PN7 is different. It stays close. It's always nearby, always within reach. This constant proximity makes it the perfect natural laboratory. And looking further into the future, a potential treasure trove of resources. Asteroids are packed with valuable materials like metals, water-bearing minerals, and carbon compounds, the very building blocks we'd need for future space infrastructure. Water, in particular, is like gold in space. It can be split into hydrogen and oxygen to create rocket fuel. It can sustain life for astronauts on long missions, and it can even act as a shield against harmful radiation. Launching water from Earth's surface is incredibly expensive, but finding it already waiting for us in space, That changes the entire game. A quasi-satellite like 2025 PN7 could one day become a cosmic gas station, a construction depot, or a stepping stone for missions venturing deeper into the solar system. This isn't going to happen tomorrow or even in the next decade, but someday it's a real possibility. And that's why scientists are so excited. The stability of its orbit means we could plan missions with precision. We could send equipment, test it, improve it, and even reuse it. We could build up infrastructure gradually, piece by piece. This isn't science fiction. It's just smart logistics. Of course, before any of that can happen, we need to know exactly what 2025 PN7 is made of. Early data suggests it might be a carbonaceous asteroid rich in dark, primitive material from the early solar system. But we'll need to get a closer look to be sure. Still, its mere existence forces us to adjust our perspective. Earth is not traveling alone, after all. We're accompanied by quiet neighbors, small companions, sharing our journey around the sun. This discovery is also a humbling reminder of how much of our own solar system remains uncharted. We've mapped the planets, named the major moons, and tracked the big asteroids. And it prepares us for what came next. Because it turns out Earth isn't the only planet with a hidden entourage. Just as we were getting used to our new companion, astronomers made another announcement in mid-2025 that sounded almost unbelievable. Saturn has 128 new moons. Not one, not 10, but 128 new moons. This discovery shot Saturn's total moon count up to 274, making it the undisputed king of moons in our solar system. These aren't giant, spherical worlds like Titan or Enceladus. They are tiny, irregularly shaped bodies, many just a few kilometers across. They are captured objects, wanderers from the outer solar system that strayed too close to Saturn's immense gravity and never left. They follow bizarre, tilted, and chaotic orbits. Some even move backward against the flow of the other moons. They are fragments, survivors, and silent relics of ancient, violent collisions. Their sheer number paints a vivid picture of the outer solar system, a place that is crowded, chaotic, and incredibly dynamic. Saturn's new fleet of moons was likely captured billions of years ago. As these objects were pulled in, they collided and shattered, creating the families of fragments we see today. Some of that debris may have even gone on to form Saturn's magnificent rings, while the rest remain as silent witnesses to that long-past chaos. With so many new moons, astronomers are now facing a rather unexpected challenge. They're running out of names. Traditionally, Saturn's moons are named after figures from Greek and Roman mythology, particularly the Titans and giants. But there are only so many names in mythology. As scientists work to catalog these new discoveries, they're reminded of a fundamental truth of exploration. Classification always follows discovery, not the other way around. We don't just find what we expect to find. We learn to expect what we actually find. As 2025 drew to a close, the discoveries just kept coming. Earth gained a quiet companion. Saturn revealed its hidden crowd. The solar system started to feel less empty, less orderly, and much more alive. And then, just before the year was out, came one final revelation. One that didn't challenge our understanding of planets or stars, but something much more fundamental. It was about us, about how fast we're truly moving through space, and how we might have been completely wrong about it all along. That story will conclude our journey in the final part. Thanks for watching. Right now, as you sit perfectly still, you are moving. Not in some metaphorical, philosophical way. No, you are physically hurtling through the cosmos at a speed so extreme it should be terrifying, but it isn't, because you can't feel a thing. Imagine it's November of 2025. Astronomers make an announcement. It's a quiet one, not something that makes headlines, but it completely overturns one of our most basic assumptions about our place in the universe. Our entire solar system, they reveal, is screaming through space at over 1,000 kilometers per second. To put that in perspective, that's more than 3 times faster than scientists had believed for decades. And this wasn't some wild guess. It came from precise measurement. To really grasp why this matters, let's take a step back. We all learn in school that the Earth orbits the Sun. It does so at about 30 kilometers per second. That's pretty fast. But our Sun isn't stationary either. It's orbiting the center of our Milky Way galaxy at a blistering 220 kilometers per second. And the Milky Way itself, it's being pulled towards nearby galaxy clusters at hundreds of kilometers per second. For years, scientists knew about all this motion. They added it all up, like a cosmic road trip calculation. The expected result was that our little corner of the universe should be moving at about 370 kilometers per second, relative to the most fundamental reference point we have. What's that reference point? It's called the cosmic microwave background, or CMB. Think of it as the afterglow of the Big Bang itself. A faint, almost perfectly uniform bath of radiation that fills all of space. It's the ultimate cosmic backdrop. If you want to measure your true speed through the universe, you measure it against the CMB. And for a long time, our measurements seemed to match the calculations. The numbers worked until they didn't. Using a global network of powerful radio telescopes, astronomers began a massive survey. They pointed their instruments at thousands of distant galaxies and listened to the radio waves traveling across billions of light years to reach us. They were looking for tiny shifts in the frequency of those waves, the Doppler effect. It's the same reason a siren's pitch changes as it passes you. A shift towards blue means something is moving closer. A shift towards red means it's moving away. When they analyzed all this data, the result was unambiguous, and it was shocking. We weren't moving at 370 kilometers per second. We were moving at over 1,000 kilometers per second. That's nearly 2.3 million miles per hour. It's a tiny fraction of the speed of light, but it's an enormous discrepancy. The universe hadn't just given us a gentle push. It had flung us forward with unexpected force. This discovery was deeply unsettling for astrophysicists. It meant something fundamental was missing from our models of the cosmos. It opened up a Pandora's box of possibilities. Maybe there's a lot more matter out there than we can see. Vast, invisible structures pulling on our galaxy with immense gravitational force. Or maybe dark energy, the mysterious force driving the universe's expansion, behaves in ways we never imagined. Perhaps there are colossal cosmic structures, bigger than anything we know, existing just beyond our observable horizon, their gravity reaching across the void to tug on us. Another idea is that we might be living near the edge of an enormous cosmic void, a vast region of nearly empty space, and the imbalance is effectively pushing us outward. It could be any one of these, or maybe even all of them combined. What makes this discovery so profound isn't just the number, it's what that number represents. We thought we had a pretty good handle on our motion through the cosmos. We were wrong. And if we were so wrong about something this basic, what else are we wrong about? It paints a new picture of the universe. It's not some static, serene expanse, gently expanding according to neat equations. It's a dynamic, uneven, lopsided place, seething with motion on scales we're only just beginning to comprehend. And yet, here we are. We feel none of it. There's no cosmic wind in our hair, no sense of acceleration, no feeling of incredible speed. That's because moving through the vacuum of space isn't like moving through air. There's no friction, no resistance. There is only silent, relentless momentum. This realization ties together so many of the great discoveries we imagine for the near future. All these discoveries point to the same truth. We are not detached observers looking in on the cosmos. We are inside it, moving with it, shaped by it, carried along by forces older and vaster than anything we can truly imagine. Our nature proves we are not special in our physical place, but we are special in one crucial way: awareness. We, on this tiny speck of rock, can measure this incredible motion. We can question it. We can be wrong. And then, through the quiet power of science, we can correct ourselves. The strength of science isn't in finding unshakable certainty. It's in embracing humility, in the willingness to be proven wrong. And that's how progress really works. Every discovery doesn't just provide an answer. It opens a floodgate of new questions. Every solution exposes a deeper layer of our own ignorance. But every correction sharpens our focus and deepens our understanding. So right now, as you listen to this, you are traveling faster than a bullet, faster than any spacecraft ever built by human hands. You are riding the currents of gravity. You are riding the expansion of space-time. You are riding the arrow of history itself. And yet, everything feels perfectly still. That contrast between the violent motion of the cosmos and the profound stillness we feel within it is perhaps the most beautiful truth of all. The universe doesn't rush. It carries us, silently, relentlessly, and forever forward. Thanks for watching. If you enjoyed this journey through the cosmos, don't forget to like, subscribe, and hit the bell so you don't miss our next exploration.